Good morning, students. We are now just continuing the previous problem. This is the second part. Say car is being used for simulation using a mounted spring. The spring is having a spring constant K is given 6.25 into 10 to the power of 3 Newton per meter. Yesterday we have calculated without having any friction. If the road surface is very smooth, if the car moves with 18 km per hour, 18 km per hour, which we took it as 5 meter per second, calculated as 5 meter per second, when it collides with the spring compresses to the maximum compression of 2 meter. This is calculated maximum compression is 2 meter, that is without friction, when friction is not there. Now suppose the road surface is rough enough and it provides a coefficient of friction of 0.5. If the coefficient of friction is 0.5, then what is the maximum compression of the spring? What is the maximum compression of the spring? Now, if the coefficient of friction is 0.5, then frictional force also opposes the motion. So this is the direction of Fk in the opposite direction. And the frictional force can be calculated by the knowledge of normal reaction. Normal reaction, if it is N is equal to mg, where mg is the weight of the car. And there are two forces acting here. One force is the spring force, Fs. Fs is equal to plus kx. So here Fs is equal to plus kx. Plus kxm. Kxm because this is the opposite direction of compression. If the compression is taking place in this direction towards left, then the spring force will be opposite to the direction of compression, right? So Fs is equal to Kxm. That's what we have taken yesterday, and we have calculated the maximum compression 2 meter. If it is providing 0.5 coefficient of friction, then we have to consider two forces. In addition to spring force, we have to consider the frictional force also. Then instead of taking conservation of mechanical energy, now we need to take work energy theorem. So by considering the work energy theorem, which states that the change in kinetic energy must be equal to work done by net force. Work done by net force. There are two forces here which are acting in the same direction. Spring force also opposing and kinetic friction also opposes the motion. Therefore, both are in the same direction. So work done by net force we need to calculate. So first let us calculate change in kinetic energy. Delta K is equal to Kf minus Ki. Final kinetic energy when the spring is totally compressed, the final kinetic energy of the car becomes 0. Minus initial kinetic energy. Initial kinetic energy is the kinetic energy of the car before colliding. So before colliding, kinetic energy of the car is given by half mv square. Half mv naught square. We can take v naught as the initial velocity. Half mv naught square. So this becomes delta k. That is minus half m. Let us take v naught square. Okay, v naught square. Now work done by net force we need to calculate. So there are two forces. One force is spring force, another one is the kinetic friction, frictional force. So that will calculate the right hand side. Work done by net force is equal to work done by spring force. We have calculated yesterday. Work done by spring force is F S dx from 0 to xm. We have calculated yesterday, if you remember, plus work done by kinetic friction Fk into the maximum displacement is xm, Fk into xm. So both are going to be negative here. So this is the work done by kinetic friction. So minus half kxm square work done by spring force. Yesterday we have calculated minus work done by Fk. What is Fk? Fk is mu n. This itself is kinetic friction. Mu k, you can take it as mu k or mu. Let us take mu. Okay. Unless otherwise mentioned, it is always, remember, unless otherwise mentioned, it is always kinetic friction. Okay. So mu n, this is Fk into xm. But what is n here? Here n is equal to mg. N is equal to mg. Therefore, work done by net force W becomes equal to minus half kxm square minus mu mg into xm. This is right hand side and this one is left hand side. So substituting this delta k value and W value in work energy theorem. Substituting, we can call this one as 1 and this one as 2. Substituting 1 and 2. Results of 1 and 2 in equation in work energy theorem. Work energy theorem statement. Left hand side we got minus half mv square minus half mv naught square, that is equation 1 should be equal to equation 2 work done by net force minus k xm square minus mu mg x. Now minus is common throughout, so take out minus common throughout and multiply throughout by 2. Multiplying throughout by 2, you can take multiplication throughout by minus 2. We get mv naught square equal to kxm square plus 2 times mu mg xm. Multiplying throughout by minus 2, we get the result. So this is of the form of ax square plus bx plus c equal to 0. Take this mv naught square inside. So thus we get kxm square plus 2 mu mg xm 2 mu mg xm minus mv naught square equal to 0. This is of the form ax square plus bx plus c equal to 0. So that we can find out the root, the value of x. We can find out the solution for x. What is x? X is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. So this is how we can substitute, so that I can find out what is the value of xm using a, b and c. So we can find out the value of xm. So what will be the value of xm now? That I will do it on the other side of the board. Thus, xm I can write now equal to minus b. What is minus b here? Minus 2 mu mg. 2 mu mg. Minus b plus, we will take plus value because negative means it will give negative value. We are taking positive value only. Therefore, plus square root of b square. B square is 4 mu square, 4 mu square, m square, g square. Yes, b square minus 4, 4 a. A is k. A is k. And c is m v square, minus m v square. So minus of minus becomes plus, minus m v not square. This is all divided by 2 times a. What is a here? A is k. So you can see here 4 is common. So if you take out 4 common, then take out square root of 4. Square root of 4 becomes 2. So 2 gets cancelled. Therefore, xm becomes equal to minus mu mg plus square root of mu square m square g square plus k m v naught square whole divided by k. So if you substitute all the values, mu equal to 0.5, m equal to 1000 kg, g you take it as 10 meter per second square. Substituting all these values, k value 6.25 into 10 to the power of 3 and v naught 5 meter per second square, and substituting the mass and constant, spring constant 6.25 into 10 to the power of 3. If you substitute all these values, we get finally 1.35 meter. Therefore, now the compression is reduced to 1.35 meter. Earlier, without friction, when the road was perfectly smooth, without friction, the compression was 2 meter. Now it is reduced to 1.35 meter. So this is a very interesting problem wherein there is the low conservation of mechanical energy. Instead of that, there is a conservation of total energy. So to solve this problem, we made use of the work energy theorem. Change in kinetic energy should be equal to work done by net force. In that term of work done by net force, there are 2 forces. One force is spring force, another force is frictional force. If you look at a spring force is conservative force and frictional force is non-conservative force. So there is a pair of forces, one is conservative and the other one is non-conservative. So when there is involvement of conservative and non-conservative force, then mechanical energy is not conserved, but total energy is conserved. Now let us see what happens to the statement of the work energy theorem if in general 2 forces are involved. So this is the end of the problem. Now we will continue. When 2 forces, one conservative and another non-conservative forces, act on the moving body. Then we write work energy theorem. In general, we write work energy theorem. That is, change in kinetic energy, delta K must be equal to work done by net force. Work done by net force I will write as work done by conservative force plus work done by non-conservative force, where work done by conservative force is integration of f dx and work done by non-conservative force, as we have found out, the non-conservative force such as friction multiplied by displacement x. So that's how we calculate work done by conservative force plus work done by non-conservative force. This right hand side gives us work done by net force. So work done by net force can be now written as work done by conservative force Fc delta x. Let us write work done by conservative force as Fc delta x, where delta x is the, let us say delta x is the displacement, plus Fnc non-conservative force, Nc for non-conservative, C for conservative, Fnc delta x. Now, by definition of conservative force, what is definition of conservative force? By definition, conservative force is that force which is a negative derivative of potential energy. So I can write it as minus delta U by delta x. Instead of writing du by dx, now I am writing minus delta U by delta x, negative derivative of potential energy with respect to position. So that what is Fc delta x I can substitute here. Therefore, Fc delta x now becomes delta U minus delta U. Fc delta x becomes minus delta U. Substitute this in this above equation. Therefore, work energy theorem now becomes delta K is equal to minus, look at this, I am substituting this value. Fc delta x is equal to minus delta U plus Fnc delta x. So this is the final form. So take this minus delta U this side. So that becomes delta K plus delta U is equal to Fnc delta x. So finally, right, this implies delta K plus delta U is equal to Fnc delta x. So earlier, if you remember, when we considered only conservative force, when there was no involvement of non-conservative force, when there was no non-conservative force, then delta K plus delta U is equal to 0, because there was no non-conservative force. When there is no non-conservative force, right hand side becomes 0. So delta K plus delta U equal to 0. It implies change in sum of kinetic and potential energy is 0 if it is involved with only conservative force. But when there is involvement of non-conservative force also, then delta K plus delta U will no more be 0. Delta K plus delta U becomes equal to work done by non-conservative force. Work done by non-conservative force, that is Fnc delta x. So that's how we are going to conclude. Okay, now that equation I will continue here. Delta K plus delta U is equal to work done by non-conservative force. So I can write it as change in K plus U is equal to work done by non-conservative force. So this I know. What is this? Change in K plus U is the change in mechanical energy. So this I can write as change in energy, mechanical energy. E represents mechanical energy. Change in E should be equal to work done by non-conservative force, where E is mechanical energy E equal to K plus U. So this is how we finally get the relation delta E equal to W and C. So delta E can be written as change in energy, final energy minus initial mechanical energy, final mechanical energy minus initial mechanical energy, final mechanical energy minus initial mechanical energy is equal to W and C, where W and C we know that is equal to F and C into delta X, where F and C is non-conservative force. Non-conservative force. So thus we conclude here that work done by non-conservative force depends on initial and final positions, and also it depends on the path, because work done by non-conservative force, like friction is a non-conservative force. It depends on the nature of the path. So it does not depend only on initial and final position. It depends on the path that is chosen. What type of path is chosen, whether it is a straight path or curved path. Therefore, this work done by non-conservative force depends on the path. It is not path independent, but it depends on the path between initial I and final position F. So thus it is path dependent. Work done by non-conservative force is path dependent. That is the difference between work done by conservative force and work done by non-conservative force. Work done by conservative force is path independent. It depends only on initial and final positions. But whereas work done by non-conservative force depends on the path between initial and final position. What path it is chosen. Is it a smooth path or rough path? It depends on the nature of the path and actual path. That is the difference between non-conservative force and conservative force. Now that is the winding up of the discussion on conservative and non-conservative forces. Now we shall discuss about different forms of energy. So we know different forms of energy. There is a heat energy, chemical energy, electrical energy. So there are various forms of energy. So law of conservation of energy states that energy can neither be created nor be destroyed. It can be transformed from one form into another form. While discussing mechanical energy, we discussed the two categories. Mechanical energy is due to motion. The energy due to the motion is called kinetic energy, and energy due to the position or configuration. Energy due to the position or configuration is called as potential energy. These are the two categories of mechanical energy. So when this mechanical energy is converted into other forms, so other forms of energy are heat energy, chemical energy, and other electrical energy, and so on. Let us study these other forms of energy. Let us study various forms of energy. Like first one we are studying heat energy. Then we study chemical energy. And electrical energy, etc., and so on. Let us first study heat energy. We have discussed a block of mass m sliding on a surface. A block of mass m sliding on a surface moving with some initial velocity v naught. When it is sliding on the surface having certain friction, then it comes to halt after certain distance. Let us say after covering a distance x naught. If this is a path and this is a block of mass m if it is sliding on this surface, then it is moving with, let us say, v naught speed, and comes to halt after certain distance, say x naught. So the distance is x naught. Then it is initially moving with initial kinetic energy Ki, and finally when it comes to halt, V becomes 0, final velocity becomes 0. So what will be final kinetic energy? Final kinetic energy becomes 0. So we calculate what happens during this motion. The motion is against the friction. There is a friction which opposes the motion. So this friction, if I call it as small f, kinetic friction, unless otherwise mentioned, when the body is in motion, sliding motion over the surface, it is always kinetic friction. So if you take work energy J, delta K is equal to work done by non-conservative force. Here is the work done by non-conservative force, because the only force that is acting here during the motion is non-conservative force, because the block is sliding on the surface. So I can write final kinetic energy Kf minus initial kinetic energy Ki must be equal to work done by the kinetic friction Fk into the distance x naught. So if you substitute this, then we get Kf is 0 minus half m v naught square, where initial kinetic energy, when it is moving with the velocity v naught, then initial kinetic energy is half m v naught square. You can write here half m v naught square, initial kinetic energy. So final kinetic energy is 0. Half m v naught square is equal to Fk. It is always opposing force. Therefore, I can write it as minus Fk x naught. So here I should write minus, since it is opposing force. Minus Fk x naught. Therefore, if you cancel this minus sign, we get finally half m v naught square is equal to Fk x naught. Means, what does it mean? The change in kinetic energy that occurs during the sliding motion is due to the work done by the friction. So to give you a simple example, in the winter, when we feel very cold, we rub our palms vigorously. When we rub our palms vigorously, there is a friction. This friction results into warmness. The palm surface become warm, so that if we touch our cheeks, we will be feeling warm. Same thing, when the block is moving on the surface, rough surface, then there will be some amount of heat is released. This amount of heat that is released is due to change in kinetic energy, that is the work done by friction. The work done by friction, which is non-conservative force, the work done by non-conservative force is appearing in the form of heat. So that heat is due to change in kinetic energy. This is how we need to understand. Whenever there is a change in kinetic energy, whenever there is a movement, change in kinetic energy, is it not change in kinetic energy? This change in kinetic energy is resulting into work done by friction, and that work done by friction results into energy that is lost in the form of heat. Energy that is lost in the form of heat. So this is how we study heat. In general, how do you define heat? We are going to learn in thermodynamics separately. Heat is defined as that transferred amount of energy from the hot body to the cold body. Heat is the transferred part of energy from a hot body to the cold surrounding. This is how we define heat. And this heat that is developed on a surface or in any liquid, it is basically due to the movement of the molecules. The movement of the molecules. When the molecules are rubbed against each other, the change in kinetic energy is converted into heat. The kinetic energy of these molecules is appearing in the form of heat. For example, if you heat the water, say about 10 kg water to its boiling point and keep it for cooling. So it will lose the energy. If it is kept for cooling for about 10 degrees Celsius, it will lose an energy of the order of 42,000 joules. 42,000 joules. I am saying example of 10 kg water. 10 kg water means suppose you have taken 10 liter of water and heated it strongly so that it is a hot water. Now if this hot water is allowed to cool by 10 degrees Celsius, let us say it is allowed to cool from 100 degrees Celsius to 90 degrees Celsius. It is losing temperature of 10 degree. So when it loses temperature of 10 degrees Celsius, then the amount of heat that is lost to the surroundings is about 42,000 joules. How is this 42,000 joules in 10 degrees Celsius loss of temperature? We are going to learn separately in thermodynamics. Okay, so that is about heat. So heat is basically due to the molecular movements, the kinetic energy of the molecules of the system, that is leading to heat. The next one is chemical energy. Chemical energy is another important form of energy which we use in our day-to-day life. If we want to cook food in the home, we use the fuel, and when the fuel is burned on the bursten, on the bursten, when the fuel is burnt, the flame of that fuel releases the heat. Using that heat, we cook the food. So the fuel is having that chemical energy. What is that fuel? The fuel is basically maybe a natural gas, right? Methane gas, ethane gas, natural gas. You are going to study in chemistry in detail. So these gases are having molecules. These molecules are having atoms. Atoms bind together, form molecules. These molecules, they bind together, they form polymeric chains. When these polymeric chains are broken, they release heat. So these polymeric chains are bound by attractive forces. So all these atoms, molecules and molecules in the polymeric chains are bound strongly together by molecular forces. So when gas is ignited or when any fuel is ignited, then what happens? These bonds are broken and they release that chemical energy into heat energy. So this heat energy we are using for various purposes. So there are two types of chemical reactions. So an exothermic reaction and endothermic reaction. Exothermic and endothermic reaction. What is exothermic reaction? For any chemical reaction, there will be reactants. After reacting, they give rise to products. If total energy of reactants is more than the energy of products. If the total energy of the reactants is more than the energy of the products, then this difference in energy released the difference in energy is released to the surrounding. This reaction of release of heat energy to the surrounding is called exothermic reaction. So in the exothermic reaction, release of heat to the surrounding takes place. Then what is endothermic reaction? Endothermic reaction, it is just reversed. Total energy of reactants, if it is less than total energy of products. Total energy of reactants, if it is less than energy of products. Energy of products. Then what happens? Heat is absorbed from the surrounding during the chemical reaction. Heat is absorbed from the surroundings. Heat is absorbed from the surrounding. Example is melting of ice. Ice is below 0 degree Celsius. So when the temperature reaches 0 degree Celsius, ice starts melting. So if you take a tumbler filled with ice cubes and keep it outside on the table surface, slowly you will find the water droplets on the surface of this tumbler or on the surface of this beaker. If you touch the surface, it will be very cold. So heat is absorbed from the surrounding. When the heat is absorbed from the surrounding, then the ice melts. So melting of ice is an example of endothermic reaction. And exothermic reaction, you can write the example of burning of fuel. Burning of fuel, which releases heat. Burning of wax candle releases heat. So in the next video we will study about the electrical energy, which is a very essential part of our life, and then we will discuss equivalence of mass and energy. E equal to mc square. Einstein's equivalence of mass and energy, E equal to mc square, and we will solve some problems based on that. Thank you. Have a nice day. Bye.